Here's a more challenging projectile motion problem that involves a lot of algebraic manipulation. But if you find yourself interested in baseball, it might be fun to do. So we're looking at the Guinness Book of World Records entry for the longest home run ever measured. And it was done by this guy here, Roy Dizzy Carlyle. And as you can tell, since the picture is in black and white, this happened quite some time ago in the early 1900s. So we're told that the ball traveled 188 meters. Oops, pardon me, we'll use the brush. 188 meters before landing on the ground outside of a ballpark. And part A says if we assume the initial velocity is in a direction 45 degrees above the horizontal, and if we don't care about air resistance or anything like that, we need to solve for the initial speed of the ball if the ball was hit at a point 0.9 meters above ground level, and we're assuming that the ground was perfectly flat. In part B, we're trying to figure out how far the ball would be above the fence. That's 3 meters high if the fence was 116 meters away from home plate. But let's kind of focus on part A for now, since part A is a bit more involved. What's important with these problems that are very wordy, I would recommend kind of writing out everything that you are given so you can kind of digest these lengthy sentences a bit more carefully. So we have the range being 188 meters. The angle was 45.0 degrees. The initial height is 0.90 meters. And I think we can also conclude that the final position of the ball, once it comes back down to the ground, well, that should be 0. So that's something we can also kind of just surmise based on what's happening here, even though we're not explicitly told that. And this is a pretty good starting spot. I would recommend using the following equation. Y final equals y initial plus v y times t plus 1/2 at squared, with the acceleration being in the y direction. Why? Why would we use this one? Well, notice we were given this explicitly, and I think we kind of like know this the quantity explicitly as well. It's also very nice that we have this. So it's just a very good starting point. And what I'm going to do is I'm going to plug in some of these quantities. We're going to set this equal to 0. We said that the initial y position that he's hitting the ball from was the 0.9, or pardon me, that's not a very well drawn 0. 0.90 meters. The Vy, do we know this? No, not really. But we can rewrite it as the unknown quantity v that we're trying to solve for, the initial speed, times the y component, which is what? Sine of 45 degrees, times time, we don't know the time, we'll just leave that alone, plus 1/2 acceleration in the y direction, well, that's our familiar negative 9.8 meters per second squared, times t squared. So let's rewrite this and clean it up a little bit. 0.90 plus v sine 45 degrees times t. Half of negative 9.8 is minus 4.9 t squared. Now, unlike in the previous problems, we would normally have the initial velocity or the velocity at hand, and we would approach this as a quadratic expression in t. But notice we have two unknowns here, and I will underline them specifically. We have the v that we're trying to solve for, and we also have t. Well, we don't know the time that it takes for the ball to return to the ground. So let's go ahead and try to get that from another equation. In the meantime, let's label this as 1, because we will eventually come back to this. The other equation that we can use to get the amount of time it takes for the ball to reach the ground involves the range, right? Why not use what we've been given? So we know that the range can be written as the initial velocity times the x component, the cosine, so 45 degrees, times the amount of time it takes for the ball to return to the ground. And in fact, let's erase r and replace it with the value that they gave us, 188. So here we have two equations, 1 and 2, and two unknowns, v and t. So we kind of have a system of equations here that we can use to solve for v. And in fact, what I'm going to recommend doing is let's start with equation 2 here, and let's solve for t, the time. If I divide both sides of equation 2 by v cosine 45, we get 188 over v times cosine of 45 degrees is equal to the amount of time it takes for the ball to return to the ground after Mr. Carlyle here hits it. And what we are going to do is take this expression for t and plug this into the first equation. And hopefully, when we do that, if we've done it correctly, we'll be able to isolate the v variable and solve for the initial speed and answer part A. And since I'm running out of room here, I'm going to move this to a fresh page. And what does it look like when we enter that in? Well, we have 0 is equal to 0.9 plus v times the sine of 45 degrees. And we did multiply this by time, but remember we're substituting the expression in for time, which is 188 over the initial speed, v, times cosine of 45 degrees. And then we said this was minus 4.9, and instead of t squared, we have 188 over v times the cosine of 45 degrees squared. That is equation number 1 once we have plugged in the expression for t. And notice that a couple things cancel and we can simplify a little bit. We have a v in the numerator here and a v in the denominator in our expression for t. So we can get rid of that immediately. Additionally, notice that we have a sine of 45 degrees in the numerator and a cosine of 45 degrees in the denominator. which we can rewrite as 0 equals 0.9 plus 188 times the tangent of 45 degrees. Okay. Minus 4.9 over 188 v cosine 45 degrees squared. And now notice, since we eliminated v in the middle term, we have only the v in the last term that we need to isolate. And we can simplify even further here by remembering that sine of 45 degrees and cosine of 45 degrees, they're actually the same, right? They're root 2 over 2, root 2 over 2. And so if you take sine 45 degrees divided by cosine 45 degrees, which is root 2 over 2 divided by root 2 over 2, that's what tangent of 45 degrees is. So it's just equal to 1. So this imposing thing here, this tangent of 45, well, we can honestly just strike it out. It's equal to 1. We don't care. Next, let's take this term over here. Since we want to isolate v, and let's move it over to the left-hand side. If we rewrite it, it looks like this. 4.9 times 188 over v cosine 45 degrees. This quantity is squared, and that's equal to what? 188.9. Our whole goal is to isolate v. We want to get that by itself. And so, since we're squaring a v in the denominator, that means we'll end up with a v squared in the denominator if we expanded this. So how about we multiply both sides by v squared? That means we'll have 4.9 times 188 over cosine of 45 degrees. That quantity is still squared, is equal to 188.9 times v squared. So if we want to get v, we can just divide both sides by 188.9 and take the square root, and that's exactly what I'll do next. 0.9 divided by 188.9 multiplied by 188 over cosine of 45 degrees squared, square root. And when I put that in my calculator, I get the following quantity truncated to 3 significant figures, following from our problem description. In fact, let me double check here. I see 3 here, I see 3 here, 3 here, and 3, yes, so indeed 3. Going back, plugging this in, putting it into 3 significant figures, I get 42.8 meters per second. And that is equal to v. This is the answer for part A. Okay? That is the initial speed that he would need to hit the ball with at that initial height to reach that range at that particular angle. That's the answer to part A. So what about part B? Let's recap on what part B was asking. How far would the ball be above a fence that's 3 meters high if the fence is 116 meters out from home plate. Let's maybe kind of draw what that looks like. I'll do this on another fresh page. As a reminder, this is part B. So here's the ground. He's hitting the ball from, 0.9 meters above the ground. 0.9. And it's kind of taking this long arc and then returning back to the ground. There is a fence, we're told, that's 3 meters high. Okay, so 3 meters. 3.0 meters. And it's 116 meters away. And our goal, again, how far would the ball be above the fence, which is this quantity right here. Okay. How far above the fence? We will call this y above. And the ball will be located y total. And what's our goal? We want to solve for y above, which is equal to what? Y above plus 3 meters is equal to y total, the total height that the ball is at that particular range. And if we just use a little bit of algebra here and subtract 3 meters on both sides, y total minus 3 meters. So our job is to figure out what the total height would be of this ball at this particular range so that we can plug that value into this expression and figure out what y above is. That's our goal for part B. What can we do to solve for the total height at that particular range? Well, since they gave us the range, we can use this range equation. Y is equal to the initial x component times t. And since we know what the initial speed is, we solve that from part A. And since we know what this range is, 116 meters, we can solve for the amount of time it takes this ball to reach 116 meters away. That's the first part. And then once we know that time, we can plug that into a position equation and then find out what y total is. But let's do this one step at a time. So we're going to solve for the time, which is, if we divide both sides, the initial x. And what's the range here? 116 meters. The initial speed from part A was what? 42.8. So 42.8. We want the x component of the velocity, which is cosine of 45 degrees, the angle that we were told. Let's double check that. 45 degrees above the horizontal. Yes, yep. And this comes out to just be a number. Meters per second. this is equal to our time. I'm just going to leave this as an expression rather than plugging it into a calculator for the time being. Now that we know the time, like I said, this was kind of like step one. Now, step two, we want to plug this time into this equation here, which we've seen quite a few times. The initial y times t plus 1/2 at squared. It's very familiar at this point. Y final is y total. That's what we want. And in fact, we'll even just write it that way. Y total. The initial time, or excuse me, the initial y height is the 0.9 meters that the ball was hit at, plus the 42.8 initial velocity of the ball that we solved for in part A. We want the y component of it, so it's the sine of 45 degrees, and we're multiplying that times the amount of time that we solved for here in step 1. And what is that? That's 1/16 divided by 42.8 times cosine of 45 degrees. And as you can see, we're kind of taking up a bit of space. I'm not going to write the units and stuff right now. But we do have one more piece here. It's minus 1/2. The acceleration in the y direction that the ball is experiencing is due to gravity, so that's g. And instead of t squared, it's our expression for t from step 1. That's 1/16 over 42.8 times cosine of 45 degrees. And that quantity is squared. So what happens when you plug all of this expression into a calculator? What do we get? Well, I get the following. Y total is equal to 44.92 meters. Now, we're not done yet. Very important. We need to go back to the beginning and plug this into the expression and basically subtract 3 meters, because we want to find out how far above the fence is the ball, not how high is the ball, right? We need to be very careful about what they're asking. So when we subtract 3 away from this value and report it to the appropriate number of significant figures, we get 44.92 meters minus 3.00 meters to 3 significant figures is 41.9 meters above the fence. Okay, and we'll kind of box that in. And that's the answer for part B. It's 41.9 meters above the fence. And that's it for part A and part B. Thanks for watching.